I hope you recall that for circular motion, we had an acceleration. When something went around a circle, then we knew we had an acceleration towards the center. Because here's, say, that's the velocity, and then we go around this way, and that's the new velocity to v1, and we had to change directions. And so there was an acceleration towards the center, a centripetal acceleration, if you like. If there's an acceleration towards the center, we must have a net force times the center. So there must be a force that causes this acceleration. Now there's a danger here. Lots of people talk about this force as a centripetal force, which is fine, but then they make up an unknown force, a magical force that just is named that. And what you need to recognize is that whatever force causes this acceleration, we should be able to label it the same as any of the other forces we've encountered thus far. So if, for example, this is a top view of someone going around the traffic circle, right? So this is a car. This is not quite to scale, but anyway, there's a car going around the traffic circle. Then the force that provides that acceleration towards the center for a car going around the traffic circle is static friction. And the reason it's static friction is because you're not moving in that direction. It's odd. It's across your tires, right? It's a friction in this direction, and hopefully your tires are not moving in that direction. So it's a static friction force, oddly enough, and it's going towards the center. And so if we look at this car, its diagram would have weight. So mg would be into the screen, and force normal would be out of the screen, or vice versa, depending on how you want to look at the screen and the car. But the friction force would be towards the center. The direction would be towards the center. And how much friction we needed, this friction force, is going to be, what it can deliver is less than or equal to mu sub s times the normal force. So the normal force depends on the mass of the car, and the friction force that we needs to provide this acceleration. So in the x direction, for example, our friction force is going to have to equal m times this acceleration, which would be equal to mv squared over r. So as our v gets bigger, as that increases, then our friction force needs to increase. And if we ask for it to be bigger than we have, right, our normal force is given. This can depend on the surface of the road. If it's a wet road, then water on asphalt has a different coefficient of friction than dry asphalt. If we have water on the road, then this is a low number. As we go around this traffic circle too fast, we can actually slip because the direction our car wants to go is like this, and the force of friction is what's allowing it to stay on this curve. Okay, so as our speed increases, then we need our static friction to increase, which means that we need to make sure we're not exceeding our maximum, this mu s times our normal force. Okay, and certainly heavier cars with the same kinds of tires will have a higher static friction, but notice I've got an m here, so that mass kind of goes away if we just put this in as our maximum. So you'd think, hey, we win, but it really just depends. If I put in mu sub s times the normal force, mg, is equal to mv squared over r, notice that our mu needs to be equal to v squared over gr, okay, in order to make the curve. Okay, another situation where we can see what happens with force diagrams is we can look at, say, a Ferris wheel. I'm just going to look at the top and the bottom of a Ferris wheel and draw the force diagrams. So we can think of this as sort of the bench here, and you're sitting on it. So we're going to look at the forces on you. And so at the bottom, the force on you, well, obviously you have mg down. That's going to be the case at the top. You're going to be a dot right there. Same mg down. That doesn't change. Your weight doesn't change. But what does change is the normal force. Because at the bottom, you need an acceleration towards the center. So you need an acceleration that's up this way, right, to go around the curve. So your normal force provided by the seat, or if you're looking at the spokes holding the seat, the force on the spokes, needs to be up, and this needs to be bigger than this by the amount given so that I can get force normal minus mg is equal to ma, right? So that has to be the case. But at the top, I have the normal force. It actually doesn't have to be as big. There's force normal, because my acceleration in this case is towards the center. There's the acceleration is down, so this mg has to be bigger than the normal force. So you are pressed into your seat more at the bottom than you are at the top. You kind of feel like you're hovering a little bit more, okay? So your normal force, the seat force on you, is a little less, okay? Now, this becomes pretty important if you take this situation and instead of a Ferris wheel, you're on a loop-to-loop ride, right? And so you're sitting like this, okay? And then at the top, you're sitting like this. Woo. Okay, so you're going through the ride in this direction. So you come along here, you go up and you loop-to-loop around. Our diagrams are the same though, right? I've got mg, and because I've got acceleration towards the middle, I've got a normal force that's bigger. Force normal, you're pressed into your seat there. At the top, you still have an mg that's down. Your acceleration is down, and hopefully you have a situation, well, notice the direction of the normal force needs to be in this direction, right? That's force normal. So hopefully these two are set up so that they're pointing down, so you're still in contact with your seat. If instead of this, to create the acceleration, in other words, we have an acceleration towards the center, it just depends on how big it is. If we have an acceleration like that, and I need, instead, because it's a small one, I need a force up like this, a force up. Well, what provides that? The seat can't provide a force in that direction, like to hold you on, unless it's got glue or something on it. Then what has to hold you in is some kind of harness, right? A lap belt or something, or an over-the-shoulders harness, which is typical nowadays, to hold you in place. It depends on your speed, and therefore your speed, A is v squared over r. As your speed gets bigger, if you have a bigger acceleration towards the center, it's a more exciting ride, so a bigger acceleration, then we can change this, and this is a better designed roller coaster because now the normal force is the seat pushing on you, pushing you to provide that acceleration, so you're in good contact with the seat. That's the direction the seat can provide a force. So if you're going fast enough, then you have good contact with the seat. You don't need your harness to hold you. But if you're going slower at the top, if this acceleration is pretty low, then you can have a situation where you need a harness to provide that, to balance out the forces to still give you that acceleration. Okay, so you know this about these roller coasters. You come in going pretty fast here because you're going to slow down as you get higher up. So you're coming in pretty fast, so you're still going fast enough here so you're not hanging by the straps. Now, some rides actually do have you hang by the straps. Ones that are fairly slow, like a pirate ship thing that flips up and upside down, that's fairly slow and you are hanging by that. But most of these loop-to-loop roller coasters are designed so that you actually don't need that harness, hopefully.